All right, welcome back. This is the second of the acid-base videos, and so we're starting this one. The first video was all about properties of acids and bases. The second video is defining these acids and bases. So we're going to talk about some acid-base definitions in this thing, and again, we'll see how far we get. We're not going to finish. There's going to be a third video at least, and maybe one after that. So don't sit down and do them all in one day. It's a beat down. I can only tolerate listening to myself so much, so I know you can only tolerate listening to me so much. So yeah, 15 minutes of pop at these things and cruise along. We start this by talking about hydronium ions. Acidic particles give off hydrogen ions in solution, except that hydrogen ion, and it talks about it here, is extremely attractive to negative sides of particles or molecules, and so this hydrogen ion that's getting ripped off of acids, oftentimes that positive is going to be attracted to the negative side of the water molecule, and so this forms what we call a hydronium ion. So you'll see hydrogen ions sometimes. You will also see these H3O plus ions. You can tack that guy onto your 50 ions on your ion sheet. That's called a hydronium ion. So we're going to deal with that a bunch as we move forward, but you can see here that hydrogen is attaching to one of those negative lone pairs of electrons there on that water molecule. Forms hydronium ion. So this is the first definition of an acid and base. This guy's name is Svante Arrhenius. So if I have a fourth kid, that name is definitely in the running. So Arrhenius is the first guy to really come up with an acid-base definition, and this is his acid-base definition. He says an acid is something that increases hydrogen ions or hydronium ions in aqueous solution. You put it in water, hydrogen ions are going to get ripped off of that thing. You know, so we look at HCl, and when we drop it in the water, that water comes in and separates those hydrogen ions from those chloride ions, and that hydrogen ion concentration then increases. An Arrhenius base, he says, is a substance that increases concentration of hydroxide ions in solution. So same kind of thing. If you get lithium hydroxide and you drop it into water, that water is going to come in and rip that thing apart into lithium ions and into hydroxide ions. And so we're going to be increasing the concentration of hydroxide ions in solution. Good, and it shows us a couple of these things, just like I wrote down there. So there's a couple little Arrhenius acid and base kind of deals. This guy would be an acid because when he's dropped into aqueous solution, aqueous means dissolved in water, when he's dropped into aqueous solution, he produces hydrogen or hydronium ions. In Arrhenius base, when we take this solid sodium hydroxide and we drop it into water, it separates into those sodium ions, and there's our hydroxide ions, and increase in those. Down here it says which one's an acid and which one's a base. I think sometimes we overcomplicate this. That's nitric acid is the name of that. If you can say what the name is and it's an acid name, hydrochloric or bromic or bromust, and it's followed by acid, that is the acid. So this is the acid. Why? Because that thing in water would give away hydrogen ions. So he's our acid. This guy has that hydroxide group on the end of it. That means when you drop in water, he's going to increase hydroxide ions. So we have an acid and a base. We learned last video, anytime an acid reacts with a base, what do we produce? Should be salt and water. Good, so there's our water. Any ionic compound is a salt, so that potassium nitrate there would be our salt. Good, so acid and base making salt and water together is the idea there. The next slide talks about strength of acids. And what makes an acid strong, right? This is the question the kids come in with the first day of class. What's the strongest acid in the world? And they don't really mean the strongest acid. They mean what's going to hurt us the worst. But strongest acid in the world is perchloric acid. And the reason it's strong is because it fully dissociates. That perchloric acid completely changes into hydrogen ions and perchlorate ions. And so its full dissociation is what makes it a strong acid. Which means a weak acid, like hydrofluoric acid is a weak acid. Hydrofluoric acid, almost none of it turns into hydrogen ions and into fluoride ions. The reverse reaction happens way more often than the Ford reaction. So hydrofluoric acid is a weak acid because it doesn't turn into that many of these ions. If we have 100 hydrofluoric acids and we drop it into water, we have 99 hydrofluoric acids in that water solution, and initially we had 0 of these, and we may have 1 of each of those, but that's it, right? Very little of it is turning into these. That's a weak acid. Now, hydrofluoric acid is one of only 2 things in the world that eats glass, right? Its fumes are poisonous. If you get it on your skin, it's a matter of seconds that you have to remove it from your skin before you have to amputate, because it will suck the calcium right out of your bones. And so, is it dangerous? Yes. Is it strong? No. Strength, when we define strength, all has to do with how much dissociation there is. The nice part is that there's only 6 strong acids, depending on the book you look at, but everybody agrees on these 6. There's only 6 strong acids. There are hundreds and hundreds and thousands of weak acids. So when we look at strong acids, I have you guys memorize these in class. There are only 6 of them. There's 3 binaries: HCl, HBr, HI. Those are strong, those 3 binaries: hydrochloric, hydrobromic, hydroiodic. And then there is HNO3, nitric, HClO4, perchloric, and there's one, what we call diprotic acid, sulfuric. Those are our 6 strong acids. It's a question on my acid-base test that you guys probably will never see. But that's a great set of data to know, and it's an easy multiple choice question to get asked somewhere down the road. I remember this question in college because I got it wrong. Lots of times we learn the most from our mistakes, right? And so those are the 6 strong acids. You should know them. Just if for no other reason, you're going to walk into college chem at some point and you're going to have to know them. Strength of bases, it's the same thing. It depends on the extent to which the base dissociates. So KOH is a strong base because it fully turns into potassium ions and hydroxide ions. I will show you on the periodic table, if we make it back to class, where the strong hydroxide bases are, the ones that fully dissociate. But those strong bases we don't need to memorize at this point, so I'm not going to write them all for you. Generally, they're group 1 hydroxides, and the bottom of the group 2 hydroxides. Those guys are our strong bases. So there's a problem with Arrhenius's definition for acids and bases, and that problem is if the base didn't have hydroxide attached to it, then it wasn't a base. It didn't have a hydroxide. It wasn't a base according to Arrhenius. So the problem the initial problem was this guy. This is ammonia. Ammonia is a base. It has all the properties of bases. At the time Arrhenius came up with his definition, everybody knew that this was a base. But his definition didn't define this as a base because there's no hydroxide here. So as a result of that, there's a couple more definitions that are developed. Bronsted-Lowry is the big one that we use most of the time, and then a Lewis acid base we'll get to in a second. We'll define Lewis acids and bases. Bronsted-Lowry is going to be the big one. That letter there, that O with a line through it, is Scandinavian. So it's probably not pronounced Bronsted. It's whatever sound that makes, and I got to work on my Danish or my Finnish or my Swedish to figure out what it is. This is 2 different guys who came up with this acid-base definition. So this is the one we'll use most of the time. Bronsted-Lowry acid is a proton donor. It's the thing that's donating a proton away. So all of Arrhenius's acids are also Bronsted-Lowry acids, and we'll see this definition at work here in the next couple slides. A Bronsted-Lowry base is a proton acceptor. Okay, so when we talk about that hydrogen with a plus charge, hydrogen as an atom is made up of 1 proton and 1 electron. That's it. And so when you have hydrochloric acid like this and the water comes in and separates the hydrogen and the chlorine, hydrogen is leaving its electron behind. And so if it's only one proton and one electron and it's leaving that electron behind, when it's H+, all it is a proton. That's it. And so when we talk about proton donor, that hydrochloric acid is donating that proton to something else. It's giving that proton away. We write it this way. It's just a proton because that hydrogen left its electron behind. Whatever is accepting that hydrogen or that proton then is considered our base. And this solved the ammonia problem and other bases that we're dealing with that are not hydroxides. So when we look at HCl here and ammonia, that hydrochloric acid is donating its hydrogen over to ammonia because it's acidic. And that ammonia is going to accept that hydrogen, and therefore that makes it basic. So this will end up being our acid, and this will end up being our base. What are our products here? We just have chloride ions by themselves, and we now have something that should look familiar. We should have an ammonium ion on the back side. And we could draw up this Lewis structure, right? If we look at this ammonia Lewis structure that looks like this, it has that lone pair of electrons that's going to attract that positive hydrogen. So that positive hydrogen is going to latch onto that ammonia. That's where our ammonium is coming from. Good, so that's the Bronsted-Lowry base, acid-base definition. The donor of the hydrogen is the acid, the acceptor of the hydrogen is the base. So hydrochloric acid is still an acid according to Bronsted-Lowry. It just allows us, without that hydroxide being present, to understand that ammonia is a base. So here's a couple more little examples. HCl in water, what's donating the hydrogen here? The hydrochloric acid is donating the hydrogen. So HCl is the acid. H2O is therefore our base. And so we see on our product side we get chloride ions by themselves and that H3O from the hydrogen being donated over to the water. Good? So in that case, hydrochloric acid the acid, water's the base. If we look at the next one and we look at the products, what happened to water on the other side? It turned into hydroxide, right? So the water here donated a hydrogen. So in this one, water is acting as the acid and ammonia is acting as the base because it's accepting that hydrogen. These all just happen to have acid listed off first. They don't have to. Here's carbonic acid donating a hydrogen. That's why it looks like HCO3 with a minus. I don't know if you can see that minus there or not. So it's the donor, it's the acid. Water's the acceptor, it's the base. If you notice, look at water can be an acid or a base. We'll see the word amphoteric defined here on the next one of these, and so amphoteric means something can either act as an acid or a base. And then probably last slide before this video cuts off gives us monoprotic acids and polyprotic. Mono means one, protic means proton. So one proton, any acids that have one hydrogen to donate are considered monoprotic. Polyprotic, many protons, and so acids that have more than one hydrogen to donate, those would be considered polyprotic. You'll actually see the word diprotic when they have two hydrogens. You'll see triprotic if they have three hydrogens. Those all get lumped in together as polyprotic acids. So it's an easy little definition for you. It's an easy little multiple choice question to say which of the following is polyprotic or which of the following is diprotic or which one of the following is monoprotic. Good, there is video number 2. We're 22 in, 22 slides in. I did better that time. I will talk to y'all later. Man, it is April 4th, I think, and it is nasty outside, rainy and cold. It's not a prolonged spring break weather, that's for sure. Anyway, we'll see you soon.